derivatives are powerful. Using the technique of differentiation, we can find critical points of a function, which are places where a function, where its derivative is 0 or its derivative doesn't exist. And we can classify those critical points as local minima or local maxima, or possibly neither. So in this video, we're going to work through an example where we're given a function, and we want to find the critical points and then classify them using the first derivative test, which is where there's a sign change in the first derivative, there's going to be a local min or a local max. Like, for example, if you're going up the top of a roller coaster, right, you're moving up and then you're going down, so you hit a local max. And then when you get to the bottom, you're going down, but then you go up, so you're at a local min. So let's do that on this particular function right here. So the first thing that we're going to do is find the critical points. We're going to find the critical points over all the real numbers. So we're not doing any domain restriction or anything like that in this problem. So we're going to consider any place where the derivative doesn't exist, or where it's 0 is going to be a critical point. The first thing that I'm going to know is that y is discontinuous, which I'm abbreviating as dis-CTS, is discontinuous at positive and negative square root of 3. Right? Because if you take either of those values and plug them in for y, the denominator evaluates to 0, and so you have a discontinuity there. So the function can't be evaluated at positive or negative root 3. So we're picking those ones up. So where does the function fail to be defined? That includes those critical points, so the function isn't differentiable there. The second thing we're going to do is we're going to compute the derivative y prime. So it's going to be classic quotient rule. So I'm going to go low d high times 3x squared minus x cubed times 2x, draw a line, and square below. Squared minus 3. Okay. And I'm going to run out of room pretty quickly on this board, so I'm going to do some things as I'm writing here, which are poor form if you're doing it on paper. So this is the derivative. I want to now simplify the thing, and then I'm going to set it equal to 0. So in principle, I want to preserve this and then do simplification on the next line, so I can go back and check whether I made mistakes. But I think the right thing for me to do is to just do simplifications by erasing. So this right here is 2x to the 4th. Okay, so then let's do the distribution here. So this expression right here should be 3x to the 4th minus 9x squared. So now I'm going to erase it and put it there. Okay. And then finally, I'm subtracting 2x to the 4ths from, I have 3 of them here. So they're going to cancel and turn into a 1, because I have 1 of them. And now I better... draw a line and square below. Danielle, draw a line and square below. And then I'm not going to write my 1. Okie dokie. All right, this looks pretty clean. I don't think I can get much better than this right now. So we want to find the critical points of this thing. So we've kind of already identified that it's discontinuous at positive and negative root 3. The square here doesn't really affect that. So that's kind of what it is. So now I want to set this thing equal to 0, and that's going to be true where c to the 4th minus c to the 9, come on, not 9, minus, minus 9x, no, c, because it's a special value, or we could go like x crit if you wanted, over c squared minus 3 squared equals 0. So this is true in general. This is a formula for y of x. This is true at some specific places, namely the critical points. And the first thing I'm going to do is multiply both sides by c squared minus 3 squared to clear that denominator. So that's going to go away. Right, and I already noted that I have those critical points. So now I'm going to move one to the other. So I'm going to move that 9c squared to the other side. And again, I'm doing this like this because I'm going to run out of room on the board. And then finally, it really looks like I want to divide by c squared. But we should note at this point that c squared equals 0 is a root of this function. So namely, c equals 0 is a double root of the derivative. So we're going to assume that c is not 0 and divide by c on both sides and find that c squared is equal to 9. And then finally, I'm going to take the square root of both sides, and I'm going to find that c is equal to positive or negative 3. So I've got these values here, positive and negative root 3. I've got these values here, and it looks like that's it. So by doing this work, I found that I have 2 more critical points at positive and negative 3. So I'm going to collect that, I think, into a table and then erase that work over there. So I've got my crit values, which I'm going to call C, and they're going to be minus root 3, 3 with a minus sign and a 3. Yeah. And what I want to do is I'm going to classify them using the first derivative test. Okay. The first derivative test. Oh, we forgot one. 0. Oh, because we had that double root. We had that double root. Right, if we plug in 0 here, it most definitely vanishes. So again, the first derivative test tells us that if the sign of f prime goes from positive to negative, it's a max, and if it goes from negative to positive, it's a min, and otherwise we don't know. So I need values between here to be able to figure out where the function y prime is positive and negative. So I'm going to draw a number line, and I'm going to go minus 3 minus root 3, 0, root 3, and 3. Noting that the function is continuous on the interiors of these intervals, having discontinuities at those other places. So I need to figure out what the value, what the SIGN sign of my derivative here is. So if I plug in, say, like minus 4, I'm going to do probably one of these, and then we'll just do the rest by calculator. So I'm going to have minus 4 to the 4th minus 9 times 4 squared. Do I even want to do this? Over 4 squared minus 3 squared. This value here is positive. In fact, the denominator is always positive. In fact, this value here, the denominator here is always positive, so it's never going to contribute to the SIGN sign. So I can just neglect it. Yeah, I'm going to do that. So that makes it pretty nice. So then I only have to think about the SIGN sign of this thing. So 4 to the 4th is... There's a way I could play this game by factoring too. I'm just gonna get the TI out because I'm gonna make a mistake if I don't. So this number is gonna be bigger. Oh, I know that this number is bigger than this number because there's only a 9 here, and I'm gonna have 16 of them here. This is 16 times 16 minus 9 times 16, so I know that this number is bigger than 0. There we go. Okay, I didn't need a calculator. Whew. Okay, so that told us that the derivative f prime is positive in that interval. And it can only change signs as it passes through one of those x values, one of those critical values. It's the only place that it can change SIGN sign is by passing through one of those things. So just testing at some value in between there is sufficient. Again, I don't need to know anything about the denominator because the denominator is always positive because it's got a square right there. So let's test in here. I know a value in here. I don't know why I made a tick mark. That's minus 2. So I'm going to play the game, same game at minus 2. So minus 2 to the 4th minus 9 times minus 2 squared is the same thing as 4 times 4 minus 9 times 4. And that value is going to be negative. So f prime is negative. Let's see here. So let's do it in here. Negative 1. That's going to be 1 minus 9 is negative 8. The function is negative. And then the thing's going to be symmetric because of these squares. Right? So I can do the same, all of those same calculations again, and I get the same values. Because these positive powers here are taking those numbers and making them be positive anyways. So it's going to be negative, negative, positive. Okay, so our function is discontinuous at these two places, positive and negative 3. So I'm going to label those with a star. So our function is discontinuous at those two places. But it's continuous everywhere else. It's continuous everywhere else. Namely, our function goes from positive to negative continuously across negative 3. Sorry, the derivative goes from positive to negative. So the function across this interval here, it must be doing something like one of those. It has to be going like that. It has to be increasing or going up, and then decreasing or going down, which means that this one here, I should have written these in a different order. Can I permute these? Is that okay? I'm sorry if you're writing along here. I'm sorry about the little change I'm going to make in this right here. So I'm going to go negative 3 minus root 3, 0, root 3, 3. Yeah. So negative 3 is a max. Let's see here. Negative 3, the function is, we've got a discontinuity. And it's going down like that on both sides. Conveniently cut off by the camera, but it's going down like that. Nope, that's not right. It's decreasing. It's coming down from the other side. Sorry, it's going like that. Because it's decreasing. It's decreasing. It's going down. I should be using pink for that. let's see, it's decreasing and then it's decreasing. So that one's going to be a neither. Same thing is going to be happening here. So it's going down, and then it's going to be coming down again. And then it's going to be going from negative to positive, so it's decreasing, and then it's going to be increasing, and it's going to stay increasing forever. And so that one is a min. I'm sorry you can't see the bottom of this thing. It just goes to like a dippy here. See it? There we go. Okay. So I feel like we should check our work. And one of the best ways that we have for checking our work is to bust out this thing right here. So I'm going to, and I would encourage you to also, let's see whether my my drawing of this function is anything close to correct whatsoever. I make no guarantees as to the correctness of this thing. So I'm going to go x to the third divided by, open a paren, x squared minus 3. And I want to make sure my window goes at least spanning this. Zoom 6 is going to get you there. Hey, I did pretty good. Let's take a, so I'm going to go ahead and erase, I think, this part here. Yeah, so I can draw a picture of what it looks like. My function looks like, this function looks like, see, I've got this discontinuity here. The function looks like it's doing that, and then it's coming in from infinity from above, and then it's going down, and then it's going to come from infinity above and go like that. That's what the function looks like. You can't see it, but see? Plot it yourself. Push some buttons on a calculator. Okay, so let's recap what we did. So we're trying to find the critical points and classify them using the first derivative test. So we're not using second derivatives, we're just using first derivatives. First, I'm going to note that the critical points include places where I have discontinuities. So I'm going to look for those right away. And then I'm going to take the derivative, which I just erased, and I'm going to set it equal to 0, and I'm going to solve that, and I'm going to find places where it's equal to 0. And that yielded this set of 5 x values where either the derivative vanished or the derivative failed to exist for one reason or another. Yeah. So that yields some partition, some breakup into intervals of the real numbers. And I'm going to take sample points from each of those intervals and feed them into f prime and figure out what the SIGN sign of f prime is on each of those intervals. And if the function is continuous on an interval and it passes from positive to negative, we know that it has to have a local max there. So we can classify -3 that way. If the function passes from negative to positive and is continuous, then it's going to yield a local min as a 3. And in the case where the function is continuous and goes from negative to negative, we get to know nothing. We'll determine that it's like decreasing and then it's decreasing, so that was like nothing. It's an inflection point. And then in the case where it went from negative to negative and negative to negative here at -√3 and √3, I'm going to use my my mental memory of what was going on right here, that the function was discontinuous there. And in fact, it was a division by 0 problem that I have something divided by 0, so it's going off to infinity. and I know that it's going down to negative infinity because it's decreasing, and it's coming off of positive infinity as it goes on the other side because it's decreasing, right? So just by knowing this partition of the interval, along with the positivity and negativity of the first derivative, I got a pretty decent sketch down here at the bottom of what my function looks like up here at the top. And I feel like we classified it. So thanks for watching. I appreciate your time, and I hope you have a good one. Bye.